Hello. So in the previous video, I explained the basic idea of cause and effect interpretation, and also I told you that some confounding variables could cause problems in interpretation. So here, I'm going to show you three assumptions for causal inference. When you make a causal conclusion, you need to check these assumptions. And as I said, I am not going to spend much time on mathematical details, even though I explain those notations and equations. So focus more on the intuition that I'm telling you. So think about this regression equation, and from this regression equation, I want to say x causes y. So I want to say that when x increases by 1 unit, y increases by beta 1. That is what you want from this regression model. And then we need three assumptions. One, the conditional distribution of error term given x. So conditional distribution of u given x has mean 0, can be written this way. So conditional mean of u given x is 0. And second, IID assumption. And third, no outliers, and rare outliers. So today I think I'm going to explain the first one only. The other ones will be explained next week. So the conditional, so error term, it should be expectedly 0, conditional on x. So expected value of u equals to 0 is easy to understand. Then what does this conditional on x means? We are going to discuss that later. And this assumption is required to show that your estimator is unbiased. So it's unbiased. Unbiased means your estimator is expectedly correct, on average correct. If you repeat your expectation, if you could repeat the sampling and estimation, then on average you will be correct. You don't have a tendency to overestimate or underestimate. That's why we need this assumption. Then again, what is the conditional on x implies? What does that imply? So think about this. When you have a regression line, and so for 15 and 20 and 25, there must be a group of school districts at each level. So at 15, you will observe a lot of school districts who have x equals to 15. And similarly, like at 20, there must be a different group of many school districts. And at 25, another group. And each group will have their own distribution. That is the conditional distribution. So this distribution is the distribution of school districts, those who have 15 students per teacher. And then the school district distributed this way. And 20 students per teacher have this distribution. So the normal distribution is just assumed, you don't need normal distribution. So the graph was drawn based on normal distribution because that's the easiest way to make a graph. Anyhow, then as x changes, the distribution may change, and we are particularly interested in their mean. The conditional mean, and they are connected by a straight line. That is the regression line that I introduced at the beginning of this slide. So the expectation is represented by the line, but the deviations from those from the expected value is not included in the regression line. So the deviation is the error term, or you may interpret this as other factors. what are these other factors and what this means. So it is now, this is about an assumption, and now you need to think about this problem outside of statistics. Statistics does not give you answers to these kind of questions. So let's think about that. I made up some stories. So you may think about two different ways. There are two different types of variables you can think as the error term. For example, you can think about teacher quality, parents' income and parents' education, or student composition, or whatever, like school facility, or like say the maybe state policy, or whatever, state tax rate, whatever. All those other social, like economic or social policy variables can be included in the error term. Or you can think about the difficulty of the test. So of course, in general, both of the variables, both are included in the error term, but let's think one by one. So if you assume that the error term is teacher quality or parents' income, say parents' income, then I would say the assumption fails. So the expected value of u given x is not 0, I guess, because it is pretty clear that wealthier families have tendency to move to school districts with smaller student-teacher ratio, right? If you agree with that, then that means when x is small, if the student-teacher ratio is small, then parents' income, u, will be high. So it is not 0. So for some small x has high u, and high x has low u, low income, right? So it fails. It's not 0. Somewhere in, like say in small student-teacher ratio, in good school districts, parents' income tend to be higher, and in bad school districts, parents' income tend to be lower. It's quite obvious. Then your assumption fails. So again, it's not statistics. You have to kind of justify or counter the assumption like this. On the other hand, if you think that if you assume that the error term only includes the difficulty of the test, so say some schools get easy questions, other schools get more difficult questions, that could be also possible. If you take this approach, then I believe the assumption will likely hold. Because, like, you may think like this, I guess the test is sufficiently random. It's like randomly generated from a test bank. And then some school districts may get some more difficult questions just because of their bad luck. They were not lucky enough to get difficult questions, but it does not matter in the end because it's random and it is not based on the student-teacher ratio. So the probability of getting difficult questions or easier questions does not depend on student-teacher ratio. It's random, literally random. It's not based on X. So in this case, it is true. On average, the expectation is 0, right? You are going to get the same difficulty on average. So as I said earlier, our benchmark, the ideal situation is when you have a perfect randomized controlled experiment. So you'd like to randomly assign people to different school districts or assign student-teacher ratio at to school districts. If that is possible, then exactly you are going to get a similar case like this. So if you randomly assign the student-teacher ratio to different school districts, then like wealthier families have no choice. They have to accept a large class, and even like poor families may have a chance to be in a smaller class. So in that sense, like no matter how rich or how poor your family is, the probabilities are the same. So in that sense, it is random, and the error term is conditionally zero. Conditionally zero. That's the idea behind it, and very important idea, very important assumption. So, but the problem here is whether this assumption is true or not is not a statistics problem. So that's more about economics and understanding the background, understanding the institution, and understanding why people behave that way. So it's more economics, and that's why economics have its own statistics. Okay, so I'm going to stop here, and next week I am going to finish this slide before doing stata. I'm not sure how long it takes to get stata, so I will keep you posted, so don't worry about that. And thank you for watching. See you later.